I have a bit of a cold, so I will not go on very long this evening, and I won't be very loud as well. My name is Claude Playmate. I'm the Activities Director here for the Big Bear Valley Astronomical Society. I'd like to welcome you to the March 2015 installment of our Big Bear Valley Astronomical Society's lecture series. Tonight I have the distinct honor of introducing my friend and colleague, Dr. John Varsik. After receiving his PhD from University of Hawaii, John has spent the last 27 years working in solar astronomy, both here at the Big Bear Solar Observatory and at the National Solar Observatory in Sacramento Peak, New Mexico. I'm sure you're all very aware, many of you at least are well aware that John wears many hats here at the Solar Observatory. John is in charge of all of our information technologies. John has written much of the telescope control software himself. He is responsible for the daily solar activity report from the observatory here. And if you are not subscribed to that report, I highly recommend you do subscribe and get the updates. And occasionally he has time to even operate the telescope. So please join me in welcoming Dr. John Varsik.
Well, this talk has kind of a catch-all theme to it. It covers a number of topics having to do with mostly solar flares and where they come from and what effects they have on us. It may be of some use to people who actually get the activity reports, because I do talk about things about sunspot classifications and what some of the mysterious numbers and letters that you see in the reports are actually talking about. Anyway, here's a little slide about the observatory here. It was built by Caltech originally in 1969, and our big dome sits at the end of causeway that's it's not really 1,000 feet, probably more like 900 feet on Big Bear Lake. And we were operated by NJIT. And the reason that we're out here in the lake is that the water acts to prevent a lot of the heating and air convection that you get above the ground in most places. Anyway, we're going to talk about space weather. Well, so what do I mean by space weather? Well, most people think of space as being this really empty place. And it basically is a really empty place. But there is a little bit of stuff in space. Very, very thin gas. And that gas not only contains neutral particles, but a lot of it is ionized, and that means that it's affected by magnetic fields, which the sun has plenty of, and that means that this ionized gas changes a bit over time, and those changes have effects on the Earth. And solar flares are the most spectacular form of space weather. I always found them kind of interesting. And space weather also has effects on the Earth. The most common effect that has been observed for thousands of years is what we call the northern lights, or the aurora borealis. And before about 200 years ago, that's all you could say about space weather, is that it sometimes caused the northern lights, and people didn't know what that was. Yeah. But what happens when we have space weather is that if we have the sun over here, we have the Earth over here, and they're joined by the sun's magnetic field, which flows out from the sun in the solar wind. As the magnetic field is pushed out from the sun by the solar wind, it interacts with the Earth's magnetic field. And that has a number of effects which were not observed up until 100 years ago, because they all have to do with affecting electrical things And we didn't have any electrical things before then. So, and also things up in space. Okay, so for example, the atmosphere and the Earth's magnetic field protect us here on the ground from the great majority of the effects of space weather. However, if you're operating satellites up in space, you don't have that atmosphere to protect you. And the interaction of the solar magnetic field and the Earth's magnetic field generates charged particles which can affect satellites in a number of ways, including damaging the solar cells on the satellites. Radiation can be dangerous to astronauts. You have the one effect of space weather is that it warms up the upper layer of the atmosphere so that it puffs up and causes more atmospheric drag on satellites, which makes them eventually fall down. As you get closer to the Earth, you find that there's this layer of the atmosphere that is ionized. It's called the ionosphere. And there are various kinds of radio signals that often are reflected off of the ionosphere for an increased range. But sometimes when you get solar flares and other kinds of space weather, the ionosphere gets disrupted so that instead of being reflected off these layers, they get absorbed by the layers. And so we have what's called a radio blackout. And also, as this layer can be disrupted and radiation can get down into the lower atmosphere, you can even get additional radiation in airline passengers, particularly those that are flying polar routes, where the magnetic field is directing downward into the Earth's atmosphere. As you get further down, there are also effects that actually affect the Earth itself. Over long distances, you get currents in the ground, which can be transmitted through power lines or through oil pipelines. And so you can get power outages and other kinds of disruptions. Okay? But all these effects have to do with technology. And up until a couple hundred years ago, none of them were observed by anybody. What happened in the early 19th century was that as more and more ships were navigating the oceans, and in those days you navigated the ocean by celestial navigation, by doing star sights to figure out where you were, and by using a compass to figure out which direction you were going. The problem was that occasionally compass needles would start fluctuating for no apparent reason. And this began to be some concern for governments in the early 19th century, and they set up magnetic observatories to try to understand what was going on. And what they found is that every so often there would be these events where over a few days you'd have the magnetic compass needle, essentially galvanometers that they were using to measure magnetic fields, would start fluctuating all over the place. They call these things geomagnetic storms. And they didn't quite understand what was causing them, but they were concerned about them. Once people began starting to use communications like telegraphs, then you started having problems with these. When you had the big solar flares, you had problems with ground currents, okay? And all sorts of strange things would happen with telegraphs. But actual solar flares remained unknown. And this is because only the very, very largest solar flares can be observed without very narrowband filters. Now, those of you who have done solar observing before will be familiar with hydrogen alpha filters, okay, which allow you to see the upper atmosphere of the sun. And they will also allow you to see a lot more solar flares than you can if you just have a broadband white light system. Now, white light flares, as we call them, are quite rare. You may get one or two of them per solar cycle. But it turns out that, in fact, the very first flare that was observed, which was observed in 1859, was also the very largest solar flare that's ever been observed. And in those days, there was an astronomer named Richard Carrington, and he would observe the sun every day by using projection. In other words, his telescope was set up to project a solar image onto a screen where he could trace the sunspots. And that's what he did here. He was doing a sunspot map, and on September 1st there was this very complicated active region that is drawn here. Okay? And then he noticed that for about 5 minutes there appeared two extremely bright patches on the sun. They're marked A and B in the drawing. And that over the succeeding 5 minutes, the bright patches moved over and to these positions marked C and D, where they disappeared. And so this was the first observation of a solar flare, and it was also the largest solar flare that has ever been observed. Now, this solar flare, people realized, was associated with the geomagnetic storm, because a couple days after the flare, there were very bright auroras that were seen all over the planet. They were seen as far south as Cuba or Hawaii. People in the U.S. Northeast were able to read their newspapers by the light of the aurora. They were incredibly bright. The telegraph systems, which were going into operation in those days, were failing. They were, sometimes the wires on the poles were throwing sparks. Sometimes the systems would operate without using any batteries, just from the ground current that was built up in the ground from the flare. There are cases recorded where telegraph stations caught on fire because of this flare. Now, a similar event, although much weaker, was observed in 1989. This event was caused by a couple flares, one of which occurred on March 9th and one of which occurred on March 10th of 1989. And this event hit Earth on March 13th, and it caused auroras as far south as Texas, not quite as far south as Cuba. And also, the ground currents in the flares blew out transformers up in Quebec, and they lost power for 9 hours. And a number of satellites went out of control temporarily because of this flare. So solar flares can be an important problem for our technological civilization. We have to learn how to predict them in order so we can have some chance of dealing with them. So getting back to the sun, okay, here's a white light picture of the sun with the number of sunspots. This one is from 1999. And you notice that the sunspots appear in these groups. We call them active regions. Now, if you look in H alpha, at the same time, it looks like this. Now you have these, you see the filaments here. And you see plage areas like this here around this active region. The sunspots don't show up as well. And so you're looking at this higher layer in the sun's atmosphere. It turns out that as you go up into the solar atmosphere, what happens is that whereas in the photosphere, the lower layer, the gas is dense enough that it pushes the magnetic fields around, basically. Once you get above this layer, the magnetic fields start pushing the gas around. And that's what you're seeing up here. And so the magnetic fields can act in these upper layers in a way that can store energy and then suddenly release it. Okay, now we're going to look at a movie. Now this movie, in fact, is from Big Bear, from the Solar Observatory, and in 1989. This is from, this starts on March 8th and goes through March 10th. And this has been available to us digitally only quite recently, thanks to a program that Professor Hyman Wang has been working on in New Jersey of digitizing all of our old films. So anyway, so over in this corner is a clock, okay, And so it's showing us the date and time of each image. And what will happen if you look over time is that all right, you see it change. You see the background change every so often. That's caused by one of the observers actually manually adjusting the filter to change the wavelength occasionally. And you'll see a number of solar flare events here. Okay, now we're still on March 8th. And this region, you'll see it's close to the limb now, and later on in the movie, you'll see it moving across the disk of the sun. This camera, it turns out, puts the solar east over here and the solar north over there, but that's just an optical problem. So this is a really good example of a very active, complex active region that's producing lots of flares. Okay, now we're coming up on the end of March 8th. Okay, and here, right in the morning of March 9th, had this huge flare. Okay. Yeah. That was a really big one. And then again, we're coming up on the end of the 9th. And then right at the beginning of the 10th, there's another big flare, which acts in a somewhat different way. So look over on this side. Yeah, there's a nice flare over here too. Now, right about now. Yeah, there it goes. Yeah. And you can see the whole region kind of lets off. Now, both of those flares were what we call X class. Although they were not the biggest flares of the month. Both of these flares are what we call X4. There was a flare back on March 6th when this region was right at the limb that was like X15. So there's more. Yeah, there's a lot more of this. We'll have to move on. Okay, this is our full disk telescope here, and it's what we use nowadays primarily for solar flare patrol work. In the old days, essentially a similar telescope to what's in here was actually mounted on the side of the telescope in the big dome, and so this dome was only put in when we built the new telescope, and we didn't have room for the flare patrol telescope anymore. So, what are sunspots? Well, sunspots are these dark things that appear on the sun, and the bigger ones like this one can be several times the size of the Earth, and they are magnetic field features. They are places where you have a strong magnetic field coming up or going down in the sun. They were the first features that were observed on the sun, and they've been observed for a very long time. The first recorded observation of sunspot was in the 4th century BC. When you get a really big sunspot and you look at the sun, say, just when it's rising or just when it's setting, and you're looking through a lot of cloud or fog or something, but not so much as to make it completely invisible, sometimes you can see when there are very large sunspots on the sun. This is how sunspots were observed at this time. That's the only way you could do it. Chinese astronomers were making fairly regular observations of sunspots beginning in the 1st century BC. Again, only looking at naked eye sunspots, so I could see. And so here are some of the details of the sunspot structure. The sunspots consist of an umbra, which is where the strongest magnetic field is, surrounded by a penumbra, which has this fibrous appearance. And then out here you have the quiet sun, which is this granulation. In detail, the penumbra looks like this. The granulation is like that. Again, sunspots are magnetic features. This is some old data from in those days we had a what we call the digital magnetograph. And you see that here you have this sunspot corresponds to this strong north field, and this area over here corresponds to this strong south field. Now there are two ways that we classify sunspots. And the first way is this rather complex method of classifying sunspots by their visual appearance. And the method that's used nowadays is called the modified Zurich classes, or the Macintosh classification scheme. And although it does have its uses, it's rather complicated, and in terms of predicting whether regions are going to have flares or not, it's a lot less useful than the other way of predicting, the other way of classifying sunspots, which is by their magnetic configuration. Okay, here's the Macintosh method. They have 3 letters. The first letter corresponds to the size of the group. The second letter is the largest penumbra and largest spot, and then the distribution of spots. It's all very complicated. The Mount Wilson sunspot configuration is what you'll see in the activity reports. Okay? And it's based on basically 2 classes of sunspots, really. An alpha spot is all the spots in the group are one polarity. The other polarity is there, but it's diffuse and isn't making sunspots. Okay? Beta is a bipolar group where you have spots of one polarity and the other polarity. Beta gamma is a group that's more or less beta, but where the spots are kind of a little bit mixed up. There's another class called delta, which is where you have spots of opposite polarity within a common penumbra. And that's the class that's most likely to cause flares. So here's an example of how one would classify a complex active region. This is from a Mount Wilson spot drawing. At Mount Wilson, they actually use a high-resolution spectrograph to actually visually measure the magnetic fields of the sunspot umbrae. So these letters and numbers here correspond to the direction of the field. R, I think, if I remember, is north, and V is south. And those were determined by which whether the spots were displaced in the red or violet direction on the spectrograph. And then the 15, and then the numbers correspond to the magnetic field strength that they measured in hundreds of Gauss. And so this spot group has, and then there's also these indicate where on the sun the spot is. Okay? So this is a very complicated group, but what you notice is that you have that most of them are V spots in this penumbra here, except for this one here. This one is an R spot. Okay? And then there's also R spots over here, as well as this one. So that makes this a beta gamma delta region. Now, this is from a Mount Wilson drawing, but of course, if you have a magnetic field map made in some other method, you can also classify the sunspots using that. Sunspots appear, and the number and positions of sunspots on the sun change over time. We'll talk about this a little later. Basically, when you have, there's this increase and decrease in the number of sunspots over time. This is called the solar activity cycle. And when you have a lot of sunspots, like in this time, the spots will all tend to be fairly close to the solar equator. When the number of sunspots is very low, you don't see any. Okay. When the new cycle begins, the groups of new spots will form at high latitudes, and then later on, as the cycle progresses, the spots move closer to the equator. And we think this has to do with how the magnetic fields are changing inside the sun. So what is a solar flare? A solar flare is a sudden release of energy in the outer atmosphere of the sun, up in the corona. When you have this sudden release of energy, which is caused by the magnetic field up there suddenly changing its configuration, you have X-rays and gamma rays are produced along with charged particles being accelerated. When the charged particles that are accelerated actually hit the surface, this is not what I want to see yet. When the charged particles actually hit the surface, or the lower level of the atmosphere, the chromosphere, that's when you get the brightening in H alpha, because the temperature up in the chromosphere, up in the corona where the flare happens, is too high for H alpha to be produced. So you don't see it in hydrogen alpha there. You have to get the particles transmitted down to the chromosphere so that you can see them in hydrogen alpha. I like to tell people looking at the sun, at solar flares in hydrogen alpha, is kind of looking at the tail of the dog. You're not seeing the dog, you're seeing the tail. Okay? So you see a tail, well, you know there's a dog there, but you may not know exactly what kind of dog you got. Now, the particles that are produced by the flare can also hit the Earth directly. When you get this kind of a strong stream of particles hitting the Earth, we call this a proton event. The flare also can trigger a blob of gas moving up from the sun, which moves a little more slowly. This is called a coronal mass ejection. There are a number of other ways you can make coronal mass ejections, other than from a flare, but it turns out that in general the largest flares also produce coronal mass ejections. The coronal mass ejections don't always hit the Earth. Okay, again, this is what a solar flare looks like with a slightly more modern telescope arrangement. Okay. And going back to our 1989 spot group, here you can see this is an H alpha image again, and there's our complex active region up there. And here's the same region in white light. And so again, you have a large complex sunspot group. Now, the solar flares, in fact, are not, although there are ways of classifying solar flares by the hydrogen alpha emission. Again, like I was just saying, that's kind of like classifying the tails of the dogs. Okay? Because the bulk of the energy of the flare is produced in X-rays. And so nowadays, when we classify flares, this is how we classify them by the amount of X-ray flux they produce in a specific wavelength. And we give depending on how much flux they produce, we give them these letters. And so an X-class flare will be a flare that has more than 10 to the minus 4 watts per square meter of X-ray flux. Now, we could go into how that relates to the total amount of energy produced by the sun and so forth, but that would be another story. Okay, now in terms of solar flares. Now, remember I mentioned that those two flares that we had in that movie that we saw, those were both X4 flares. They looked rather different in H alpha though. The first one that we saw was much brighter, although the second one covered a larger area. But they were both X4 events. However, the largest flare that's been observed in modern times, by modern times I mean since the space age began, and we had X-ray flux monitors, was actually this event from November 4th, 2003. That event was initially estimated to be X28, and later on they revised that to be X45. The problem was that it saturated the detectors, and so it's rather difficult to figure out exactly how bright it really was. Unfortunately, this event, the reason why I don't have a better picture for this is there are two reasons. One is that it's at the end, it's when we sit, I'll show the movie in a minute. It's right at the edge of the sun, so which makes it a little hard to see with telescopes. And the second reason is that this was the day after we came back to the observatory from being evacuated during the old fire, which happened at the end of October 2003. So here's the movie. You can see here's the flare. This movie is looping, so it's going to do it again and again. It's all right there. Okay, so going back to coronal mass ejections. Coronal mass ejections occur when the magnetic field in the corona suddenly changes from this configuration where the loops are closed and the material is confined into a configuration where the material is released and can escape from the sun. And you get a big blob of coronal gas ejected from the sun at relatively high speed. By relatively high speed, I mean it can reach the Earth in 2 or 3 days. CMEs can come from flares, and the largest ones do. They can also come from filament eruptions. In other words, the filaments are those long, dark features that you see moving across the face of the sun in hydrogen alpha, and they're the same thing as what you see as prominences at the edge of the sun. Of course, in order to affect the Earth, they have to be moving in the right direction, which they aren't always. This is what one looks like. Again, this is a coronagraph out in space, so it has a disk that's covering up the sun, which is indicated by the circle here. And so you have this big blob of material out here, which is moving outward from the sun. This is not an event that's pointed at the Earth, by the way. Now, as I said, the coronal mass ejections are often caused by filament eruptions. And here's what a filament eruption looks like. Now, it turns out that, again, filament eruptions are caused by a different kind of magnetic reconfiguration. Occasionally, a filament eruption like this will also produce a flare. These are what they call Hyder flares. And they are a little different from the flares that you get from active regions in that they generally are very long duration events, but usually not very bright. The CMEs are the things that can interact with the Earth's magnetic field because they're a big blob of gas that's charged and has a magnetic field. The shock wave from the CME hits the Earth's magnetosphere and squashes it on the day side and extends the night side field out. And again, because you're changing the shape of the field, you can get reconnection. And that causes energy to stream down to the upper atmosphere of the Earth, especially in the polar regions. You can see here's a not very good diagram. You have the solar wind pushing on the Earth's magnetic field, which stretches it out into this elongated shape. You can have the particles from the CME have a shock along here and stretch out the field along here and make the field reconnect here. And that will drive charged particles along the field lines back to the north and south poles of the Earth, which is how you get the auroras. It turns out that the orientation of the magnetic field in the CME is critical. If we go back to this previous slide, if the magnetic, suppose, all right, you have the north and south poles of the Earth, okay? So the field is moving like this. If we have the magnetic field in the CME is moving this direction, then when it hits the Earth's field, they repel each other. If it's the other direction, they attract each other. When they attract each other, it's kind of like you're opening a hole in the Earth's magnetic field. And so you get a much stronger effect between the CME and the Earth's field. The south-facing CMEs produce much stronger effects than the north-facing ones. The only way you can reliably tell the orientation of the field, though, you can't really tell from looking at the, at least most of the time, you can't tell from looking directly at the active region where the CME came from. It's not as reliable as actually looking at the orientation of the field as it is in space. So there's a satellite that's located about 1.5 million miles closer to the sun than the Earth, and it actually measures the magnetic field in place. So as the CME goes past the satellite, it measures the field, and it can radio us and tell us which way it's pointed. So this is a satellite called the Advanced Composition Explorer. It was launched in 1997. It was meant to last for 5 years. It's still there, fortunately. Fortunately, right now, it's being replaced by a satellite that was just recently launched, which is called the Deep Space Climate Observatory. And it's being slowly right now moved out to the L1 Lagrange point. And once it gets there, it will be able to replace the ACE satellite in performing this function. Now, the solar flare effects on Earth, there are 3 basic kinds of effects. There's the immediate effect of the X-rays and ultraviolet radiation. Okay? This causes primarily radio bursts and disruption of the ionosphere, which can cause radio blackouts. The proton events approach later. They can take anywhere from half an hour to several hours to go the distance between the sun and the Earth. They move very quickly. And these again cause, among other things, radio blackouts. The CME events can take 2 or 3 days to reach the Earth. Not all flares produce CMEs, and whether a CME will hit the Earth or not depends on exactly how the CME is emitted from the sun. In general, these 2 events are only going to be significant in terms of hitting the Earth if the flare occurs on what we call the western side of the sun. In other words, after the active region has passed the solar meridian. This has to do with how the magnetic field in the sun is connecting that portion of the sun to the Earth. The immediate effects from the X-rays and gamma rays, you get radio interference, you get a radio blackout. They can also affect GPS signals. It will heat up the ionosphere. It will cause drag on satellites. And you can have radiation danger to astronauts. The delayed effects, the proton storms, normally take a couple hours to reach the Earth, but sometimes they'll be a lot faster. Proton storms will cause charging events on satellites so that the chips in the satellite's computers can have bad bits put in them, basically, arbitrarily, which can cause the programs to crash or the memory to be corrupted and all sorts of other things. Normally, computers in satellites, electronics in satellites are all shielded. They're put inside a fairly thick metal can, but that's not always good enough. And again, you get radio signals blocked, particularly in the polar regions. This can affect communications with aircraft that are on these polar routes, for example. Once an airplane is far enough away from populated areas, the VHF radio that they normally use to communicate with the ground doesn't work because the VHF radio is not reflected by the ionosphere. And they have to switch to high frequency radio, which is, but that high frequency radio will be blocked by when these CMEs happen. And so what will often happen is that when a strong CME is expected, airlines will reroute the traffic to lower latitudes. Of course, if the proton storm is large enough, then you'll get higher radiation exposure, which would also cause the airlines to reroute their flights. But in general, they reroute them sooner than that because they want to avoid communication problems. Now, when the CMEs hit the Earth, those effects are probably the most important for most people. CMEs cause strong auroras. CMEs will cause strong currents in long-distance power lines, which can destroy power transformers. And CMEs can also disrupt satellite operation. So how often do flares occur? And as I said, the flares generally come from the active regions, these big groups of sunspots. And as we saw earlier, that the number of sunspots you get depends on the phase of the solar cycle that you're in. To produce a large solar flare, you need a big active region with a complex field. Large complex active regions can occur at any time in the solar cycle, but the likelihood of such a region happening depends a great deal on the part of the solar cycle that you're in, and also the strength of the cycle that you're in. I like to think of solar cycles as being kind of like hurricane seasons on Earth. You know, on Earth we have, in the Atlantic Ocean basin, they have a hurricane season between June and November, okay? And it peaks in around September. So that the biggest number of hurricanes will be in September and October. But you can get hurricanes anytime during the season. And it's possible for a very strong destructive hurricane to occur at any time during the hurricane season, although it's more likely to happen in September or October. Well, solar flares are a bit like that. They depend on these big active regions, and the big active regions primarily occur during the peak of the solar cycle. And the number of active regions you get depends on where you are in relationship to the peak of the solar cycle, and also in how strong the peak is. Solar flares are not easy to predict. Basically, we don't have the kind of computer modeling that meteorologists use to predict weather on Earth. Okay, so we have to rely more on methods having to do with just the experience of the observer and being able to identify these complex sunspot groups. And even then, that doesn't tell you, that just tells you how likely a flare is to happen. It doesn't tell you exactly when it's going to happen. It could happen in 5 minutes from now or a day or two from now, and you don't really know. So the sunspot cycle, this maximum and minimum of the number of spots, has been observed since the 19th century. Since then, we've gone back through the old records of people's sunspot drawings and observing records to take it back to the time of Galileo, when the telescope was invented. And we have this plot. So here we have 400 years of sunspot observations up until about 2010. So this is back in Galileo's time here. There was this long period in the latter half of the 17th century when there were very few spots observed. Okay, the numbers are very low here. Okay, and then it picks up again. And since that time at least, there's been this pretty regular 11 or 12 year activity cycle, which has continued up until the present time. You'll notice that the strength of the cycle varies a lot. Okay, the biggest cycle, which happened around 1959, is over here. But we've also had very weak cycles like the ones at the beginning of the 19th century, which were very low sunspot numbers. Okay. Now, exactly what happened in this area, considering this is all the data we have to work with, so it's hard to say exactly what happens when you're going into this period based on this data. Now, about this period, this Maunder minimum, by looking at proxy data, in other words, looking at indirect measurements of solar activity, we've been able to determine that the sun normally has periods like this, maybe roughly a third of the time. And we've also looked at other stars that are similar to the sun, and stars that are about the sun's age behave pretty much the same way. About a third of them are in this minimum phase, and the rest of them have more or less greater or lesser levels of activity like this. Okay. So here are the last few cycles, kind of in a larger scale. This is the 1959 peak here, okay, and then this is the current cycle, and this is our current data right here. Okay, so what you notice is that our current cycle that we're in is much weaker than the other ones have been since space travel has been in existence. And so exactly what will happen in the future is open to question. There are some indications that suggest that the next cycle, in other words, the cycle that we're in now, we're coming to the end of it. Where the period that we're in right now corresponds to this phase in the earlier cycle. And so we're going to see, over the next year or so, we should see a pretty rapid fall off in the number of sunspots. Okay, and it should drop down gradually to some low level. Will it be this low again? We don't know. There are some indications that suggest that the cycle after the one we're in now will be weaker than this one. And I feel fairly confident in saying that, or at least as confident as anybody can be. One of the more embarrassing things about solar astronomy is if you get a bunch of astronomers together to have a meeting about predicting the next solar cycle, they will issue a number of predictions which will all be wrong. So bear that in mind. It's quite likely that I'm wrong too. But I would tend to think that the next cycle is going to be weaker than this one. How much weaker it will be, I don't really know. Are we going into a new Maunder minimum phase? I don't know. Maybe. Maybe not. Now, in terms of where you can get space weather information, the official forecasting center for space weather in the United States is the NOAA Space Weather Prediction Center, which is in Boulder, Colorado, and they have this website, and they issue forecasts and watches and warnings just like the National Weather Service does for Earth weather. Okay. And they use a set of scales to talk about the severity of particular events, which I'm not going to go into here. The reports that I give are specifically about solar flares. NOAA also will talk about geomagnetic storms and CMEs and other features of solar activity that I've not gone into in this talk. How concerned should we be about solar flares? Well, we know that estimates have been made that if a Carrington type event were to happen today, that due to the effects on power distribution, that you could have $1 trillion worth of damage in North America if such an event were to occur. Mostly having to do with transformers being blown out. And this could be very bad because these transformers that we were talking about, these are all custom-made items. You can't just go into Harry's transformer shop and buy 5 of them. It takes like 6 or 9 months to build one. And you can't just get them off the shelf. So if such an event were to occur, it might be very disruptive to a lot of things. Fortunately, it appears from the indirect proxy data that events like the Carrington event are rare and perhaps only occur once every 500 years. And also it seems that at least from the indirect data that we've looked at so far, that events larger than the Carrington event don't seem to be very likely, and none have been detected. Flares are not a direct threat to our lives. We're protected by the magnetic field of the Earth and the Earth's atmosphere. Even if you get an extremely large event, we ourselves are not vulnerable to them. Our technology is. Okay? And so when we are building systems like power distribution systems and satellite systems and so forth, we need to take that into account in designing them. But they do not, they're not a direct danger to ourselves personally. Do flares affect weather or climate? Individual flares probably don't. But the sunspot cycle probably does to an extent. We know that the total energy output of the sun is slightly larger at solar maximum than it is at minimum. So for example, that would suggest that if we have a long period with no sunspots, that the solar flux would tend to be low for a long period of time. And that could have an effect on the climate. But here again, that's another story for another time. And that's about all I have today. So are there questions?
Yes.
Yeah.
Okay.
This last Aurora thing that occurred this week.
Well, that was an interesting event.
Let me just finish my question. The news reports indicated that it was a surprise. Was it a surprise to you?
Well, it was in a way, because this particular geomagnetic storm seems to me to have been a combination of things. Geomagnetic storms are caused, as I mentioned, by CMEs, but they are also caused by another phenomenon on the sun called a high-speed solar wind stream. High-speed solar wind streams are streams of material that come out from what are called coronal holes on the sun. And what I suspect has happened with this particular event is that we had CMEs from a couple of rather moderate-sized flares that combined with a high-speed solar wind stream and with a strongly, and both of these things are strongly south-pointing. So you had, and that magnifies the effect. And so that's why you had this big geomagnetic storm. So it was a bit of a surprise to have all those factors together.
So even the satellites didn't see it coming, basically.
Right. So the NOAA didn't expect this strong of an event. Yeah.
You mentioned that the '03 event was upgraded from an X28 to, I think you said X45?
Yes.
I'm aware of that. Fortunately, that was at the limb and was not pointed our direction,
Right.
unlike the Carrington event.
Yes.
Could you compare the magnitude of that to estimates of the Carrington event?
It may have been comparable.
Which kind of differs with the estimate of a Carrington event possibly happening once every 500
On the other hand, we don't really know what the X-ray flux from the Carrington event was. Okay, we don't have. There's no real way to know that for sure. So.
But I think it's safe to say, follow-up, that if that '03 event had been pointed our direction and had the proper magnetic orientation,
It could have been a.
it would have been a bad day.
It would have been a bad day. Yeah. For somebody.
When you have a white light flare,
Mm-hmm.
generally a very large event.
Yeah. Well, generally, in order to have a white light flare, you have to have the. I talked about those particles coming down to the chromosphere to heat up, to brighten up the H alpha. In a white light flare, they come down to the photosphere. And so that's how you get it in the continuum, in white light. So in order to have a white light flare, you need to have a very strong event, strong X-class flare, and it needs to be with the proper orientation of the fields so that you get the particles streaming down to hit the photosphere. As I mentioned before, if you can have two flares of the same X-ray class, one of them will be much brighter in H alpha or in white light than the other, simply because of the configuration of the loop structure.
John,
Yeah.
how would we see a white light flare? Does it have to be on the limb? Or
No,
What would it look like on the disk itself?
it would look like a sudden brightening of the photosphere compared to the region around it.
So Carrington was making a drawing and the flare
Yeah.
occurred while he was making the drawing, and
Yeah.
it lasted like 5 minutes,
Yeah.
and it was gone.
That's the other thing, of course, the white light portion of the flare will be at the very brightest part. Okay, and so that's usually only over a few minutes' time.
Have you seen one? Have you seen one?
Have I seen a white light flare? I think I did see one once. I think it might have been one of these March '89 flares. It was a long time ago.
Can we learn anything? This is a totally different subject. There are
Yeah.
some stars that are flare stars.
Yes.
But can we learn anything from them since they're,
Well,
they have a different frequency of flares? Some of them have them all the time.
some of them have them all the time. And we think that the thing that's driving magnetic activity in stars has to do with the differential rotation inside the star, which depends on the difference in the rotations between the equator and the poles, but also just on the speed of rotation. All these flare stars rotate very rapidly. And so they have a lot more energy available. The sun, for example, produced a lot more and much brighter flares when it was only 500 million years old than it does now. This is because over time, the magnetic field going out from the sun has been slowing the sun down, its rotation. And so when the sun was very young, it was very active, and it produced lots of big flares. In fact, it didn't. What we observed from looking at stars like the stars in the Pleiades or in the Hyades, which are much younger stars than the sun is, that they're active all the time. Okay, and they don't have cycles; they're just active all the time. And so the mechanism that's generating the activity is somewhat different in these stars than it is in stars like the sun, in terms of the actual how the magnetic field dynamo is working is slightly different. But yeah, we do learn some things from that.
John, I wonder if, I'm not sure I understood the question nor the answer just now, but how do we know that there's a sunspot cycle on a star, other than our own star here? Is it on X-ray emissions?
Well, in some cases we use X-ray emissions. The classical way of doing it is that, I didn't mention it here, but also if you observe the sun in the calcium K line, that you know that when you observe the sun in calcium K line, you'll see all the bright plage areas where the active regions are, and then the rest of it will be fairly uniform. It turns out that you can, with a narrowband spectrograph setup or with a narrowband filter setup with a photometer, you can actually measure this variation in the calcium K emission in other stars, and you can compare it to measurements that have been made of the sun, where you integrate the light from the sun and look at the sun as a point source, like a star. And what you find is that although the sunspots themselves are harder to measure because you're talking about a very small variation in the light level, this K-line index can be measured fairly easily. And there was a special program that was done at Mount Wilson, in fact, for about 25 years, between about 1965 and 1990 or so, where they had about 100 stars that they used the Mount Wilson 60-inch, and they dedicated it basically to measuring the K-index from all these stars as often as they could. And that's how we know that stars like the sun behave the way the sun does. And young stars are a lot more active. And we know that in fact, K and M stars that are cooler than the sun, tend to be more active. Yeah. Stars that are warmer than the sun, F stars, tend to be less active. Although their activity, the F stars, it tends to be fairly uniform and decreases somewhat as they get older. F stars don't last very long, and so they're all young stars compared to the sun. There's more variation in the K and M stars because some of them are young, some of them are very old. So that's how we know about activity cycles on other stars, primarily.
When a CME erupts, when that ejective is heading towards the Earth, let's say,
Yeah.
the alignment of Earth and trajectory of the CME, does that change at all?
Well, the CME is moving out from the sun, and it's moving in this kind of, you can think of it as kind of a spiral path. And so it moves out from the sun, and hits the Earth
So
eventually.
the instantaneous view doesn't necessarily say the CME is going to hit the Earth then?
Well, you can tell pretty well from an instantaneous view, say from the LASCO, you're thinking of the LASCO coronagraph on SOHO, which lets you see the CMEs. And you can tell when they're headed in our direction, or directly away from us, depending. And that's a pretty good indication that they're headed this way. You don't know for sure that they're going to hit, really, until they hit the ACE satellite and you actually see the sudden shock as the magnetic field suddenly changes and you see the blob of gas coming by. The Earth is a pretty small target. Okay?
And how wide is the CME as it goes out? You mentioned
They get pretty big. And the
20
CM,
or is that
yeah,
diameters?
yeah.
Yeah.
Oh yeah. Yeah, they get very large, and I mean the amount of material in total is very large, but the density of material is still pretty small. Yeah,
Where does that material end up? It just keeps passing?
it keeps going. Okay, it becomes part of the solar wind in general.
Is that where the particles are in space, are coming from maybe other?
In other words, the sun is emitting particles all the time.
Right.
As we call the solar wind. The CME, and looking at it from one point of view, is kind of a hiccup in the solar wind. Okay, it's like kind of a belch in the solar wind or something, so it's in terms of the total amount of solar wind, it's not a big deal. Yeah.
The Voyager spacecraft,
Mhm.
about 3 years ago, was defined to have left the solar system.
Yeah.
There were several discussions of it.
Oh, and people are still talking about exactly what that's happened.
I assume that the instruments on the spacecraft are looking at the sun and measuring particles.
Well,
When you decide you've left the solar system, it's because you can no longer distinguish the particles coming from the sun from the background radiation in the universe.
well,
Do you know what frequencies or what type of radiation?
Well, what's happening? What's actually happening is that the Voyager spacecraft have magnetometers on them, so that they're actually measuring the magnetic field and the particles where they are. Okay.
So it's the magnetic field.
Yeah. So they
not
see.
measuring particles.
So they see a sudden change in the orientation of the field and in the density of the particles. And that says, okay, we've changed from one environment to some other environment in space. And we know that just as the solar wind, hits the Earth's magnetosphere and is deflected around it, there's a very thin interstellar wind, if you like, that's out there between the stars. Okay?
Coming from all the stars, you mean? Or
Yeah, and it's just out there.
different
Yeah, it's just out there. There's some very thin plasma out there, and the sun is moving through this plasma,
Yeah.
and so it's the same kind of thing. You have the plasma comes to the sun's magnetic field makes this bubble around the sun and the solar system, and there's a shock wave where this interstellar material is being deflected by the solar field.
Have you heard of any discussion about Voyager 2? Because we launched 2 spacecraft.
Yeah, I
haven't.
I'm not really up to date on that.
It's expected to go through magnetopause within the next year or so.
Yeah.
It's,
So if I remember, one of them is moving. Yeah, Voyager 1, I think, is just moving faster.
yeah, it's like 130 something astronomical units out, and
Yeah.
Voyager 2, I think I heard, is like 115 something.
So it's still a little behind, So
Yeah, well, they were launched around the same years.
yeah, but
One went by Jupiter, Saturn, and Uranus, and the other went by Jupiter, Saturn, and Neptune, if I recall.
yeah.
They used the gravitation of these large planets to deflect the trajectory.
right. And that also changed this, also changed the velocity.
Sure. Yeah.
And so it ended up that because of the particular trajectory that Voyager 1 was put on, it ended up going faster.
Yeah, that makes sense.
John, when you talked about the ground currents that are generated from particles coming in here, can you measure that?
Oh yeah,
If I put a voltmeter between here and somewhere else?
yeah. They can measure it on those big power lines. They measure it. Yeah. And they are working on systems to try to make the power lines less vulnerable to these things. You know, shut them down when you get these big currents, to keep the transformers from blowing out. But that doesn't always work.
Can they be shielded, or do you have to detect the
Well,
event
I
and shut them
mean,
down?
yeah, you have to.
Rather than have some sort of shield around them, either for the transformers on the Earth or the electronic.
I mean, these power lines are acting like giant antennas.
Well, I understand the power
Okay.
lines, yeah. Okay.
They act like a huge, long antenna. Okay, and so you can't really shield it.
You can't shield it, I understand that, yeah.
Time for one more question?
Well, I could keep you here longer, but you probably want to go home and eat.
I have a question.
Yeah.
You mentioned that the ACE is 1.5 million miles closer to the sun than we are.
Yeah.
So is there any way of predicting how long the warming will take to reach Earth?
Well, it's the light travel. It's the spacecraft detects the magnetic field, and then it radios to the Earth. Okay, and so the light travel time is much faster than the particles. So that gives us about 45 minutes or so warning.
What does it exactly stand for, ACE? I'm sorry.
Was Advanced Composition Explorer or something like that?
Okay, once more, let's thank John again for that.
Thanks, John.